thank you so much. So now we can move on to the next talk, which is being given by Mike Giles from Oxford. So I hope you can share your screen, yeah, on multi-level Monte Carlo methods. Thank you so much. Mike, you can go ahead. You're on mute.
Okay. Okay, is that showing correctly, the slides?
Yes, but you could make them bigger possibly, but without any...
Oh, I see, it's not full screen for you, is it?
Yes, not full screen, yes. Please go ahead. Yeah, I think it's full screen, more or less. Yes.
Okay.
It would be better if you share only the application instead of the whole screen as you're doing at the moment. I think there has been a moment of problem with his connectivity. Maybe.
Yes, I think that, Mike, are you there? Yeah, your connection has, yes, Mike has left and will come back in a second, I hope.
You're muted, Serge.
Sorry, yes, it's a good idea to show only the application, not the full screen. Yes, indeed, thank you. If we've lost Mike, we should maybe think of changing the order. Habib, you're next. But unless Mike can come back in a few seconds, I'm getting worried.
Yeah, let's give him time. I was expecting that I didn't need to spend much time introducing multi-fidelity methods.
Oh, he's back to do this. Thank you.
Yeah, Zoom seems to be crashing on me.
Yes.
So maybe you'd better run the slides there.
Yeah, I've got them already. I can run them. Just give me a moment.
Okay, sorry about that, everyone. Right, so my area of research, for the last several years has been multi-level Monte Carlo methods. And so today I just want to give you a very quick introduction to them and say a bit about the things that we've been working on most recently. So going to the next slide. Right, so this is the overview, the introduction of the method and these two areas of research from the last couple of years. So next slide. So with Monte Carlo simulation, we're interested in estimating the expected value of some quantity P. And in this talk, I'll keep it simple with P just being a scalar random variable, but the ideas here also extend to functions, usually a function of one variable that we're estimating. But to keep the idea simple, let's just think of a single scalar quantity P that's the result of some computation or simulation. And to estimate the expected value of it, Monte Carlo simulation is incredibly simple. We just take an average of n independent samples, Pn. And in order to achieve a root mean square accuracy of epsilon from that average, the number of samples we need to use scales like epsilon to the minus 2 times v, where v is the variance of the quantity p. And if each one of those samples costs c, then the total cost is approximately epsilon to the minus 2 v times c. Next slide. So the starting idea for multi-level is a two-level approach. That if there is some other quantity p tilde, which is approximately equal to p, then the expected value of p, which is the thing we care about, is the expected value of p tilde plus the expected difference, p minus p tilde. So that's very simple, trivial. What that means is that instead of directly estimating the expectation on the left, instead we can estimate each of the expectations on the right. And the point is that we can use a different number of samples to estimate the first expectation. So that's using n0 samples of p tilde, and a different number, n1, of samples of the difference between p and p tilde. Now, this particularly makes sense if p tilde can be simulated very cheaply. So later on, I'll give the example of maybe simulating p tilde using reduced precision floating point accuracy. So that's something which would be very appropriate in an HPC context. Or alternatively, if you have some driving random variables that are very hard to simulate, then p tilde may be based on approximate random variables. Now, what's the benefit here? Well, the cost of this new estimator is going to be n0 c0, where c0 is the cost of simulating p tilde, plus n1 c1, where c1 is the cost of estimating this difference between p and p tilde. And the variance of this new combined estimator is simply v0 over n0 plus v1 over n1, because each of those two expectations is being independently estimated. So if you now do a constrained optimization, so you're minimizing the cost subject to the same overall accuracy, what we end up getting is this expression for the total cost approximately. So epsilon to the minus 2 again, but now it's the square of the sum of the square roots of v0 c0 and v1 c1. And if we're in a situation where c0 is, I've got here 1/10 of the original cost of c, so that p tilde here is being simulated 10 times cheaper than the p. And if also v1, so that's the variance of the difference, is tiny compared to the original variance, then what you end up with is a much more efficient simulation. So we have a large number of very low cost simulations, that's the p tilde, and a very small number of the expensive simulations, which is the difference between p and p tilde. And so in this case, given the numbers I've presented here, that would give us a factor 8 savings compared to the original Monte Carlo. Okay, so going to the next slide. The full multi-level applies in situations where you don't just have these two levels, you have a whole sequence of different approximations, increasingly accurate but increasingly costly approximations to the true quantity of interest, P. So the context in which I first got into this work was in simulating stochastic differential equations motivated by finance applications. And so the level L, so that's the subscript of the P hat here, the level L in these simulations corresponded to using 2 to the power L time steps in the simulation. So clearly, the higher the level, the more time steps, greater the computational cost for each sample, but also it's a more accurate approximation to the true path and hence to the true value of the output quantity of interest. And so the expectation, previously I was replacing the thing I cared about by the sum of two expectations. Now we've got this whole sum of corrections between each successive level of approximation. And so that's just a simple telescoping sum, which gives us back that expectation on the left-hand side. And then we have this corresponding multi-level estimator, where on each level of simulation, it's been done independently of the corrections on the other levels. And so that's why with the P hat, I've got L comma N to indicate that it's a random sample being chosen for that particular level of correction. And then we have that expression at the bottom then for the total cost, which is very similar to the two-level approximation, but now we've got a sum over all of the levels. Okay, next slide, please. So in the context of what this means for solving stochastic differential equations, we're using a time step which goes like 2 to the minus L, because this is for a unit time interval, so we have 2 to the L time steps. And so this is our approximation of a standard scalar SDE. A is the drift term, B corresponds to the stochastic diffusion term, and B would normally be multiplying the increment of the Brownian path. Well, the increment of the Brownian path over a single time step of size HL is normally distributed with variance equal to H. And so we can simulate that as being square root of HL times Zm, where Z is a unit normal random variable. So this gives us a simulation on a fine level of resolution. And in the multi-level, we have to couple that fine simulation on level L with a corresponding coarse simulation on level L minus 1. So in level L minus 1, we're taking half as many time steps. So in my indexing here, I'm going from M to M plus 2, so that one coarse step corresponds to 2 fine time steps. And what we then have is that the Brownian increment over that one coarse time step corresponds to the sum of the 2 Brownian increments over the corresponding fine time steps. And this is the way in which we jointly simulate both the coarse path and the fine path. And that then gets fed into computing the P hat L and the P hat L minus 1, which were on the previous slide. There's then standard stochastic numerical analysis for SDEs. that shows that the variance of the final path value on the coarse level and the fine level, the difference, that variance is of order the time step h. And therefore, if what we're interested in is an output quantity of interest, which is a Lipschitz function of that final path value, then the variance of this difference between the peaks, so this is the multi-level correction term, that variance is of order h. So as we go to finer and finer levels, the difference between PL and PL minus 1 is getting smaller and smaller, actually at exactly the same rate that the computational cost is increasing as you go to the finer and finer levels. And then there's a bit of analysis that you can go through that shows that therefore, overall, we have a complexity that behaves like epsilon to the minus 2 log epsilon squared as being the computational cost to achieve an epsilon root mean square accuracy. Whereas with the standard Monte Carlo approach, it would in fact scale like epsilon to the minus 3. So you would normally have 8 times the cost to get twice the accuracy. So this significantly improves the overall complexity. Okay, next slide. So that was a very quick introduction to multi-level for those who haven't heard about multi-level before. Now I just want to say a little bit about 2 recent projects. So the first project came out of a concern in the medical area, and it's to do with the funding of medical research projects to decide which are the most cost-effective projects to undertake. So suppose we have 2 uncertain random variables x and y. So these are sort of parameters affecting the effectiveness of different medical treatments. And you're trying to decide what is the best way to treat the population, given that there is uncertainty in the effectiveness of different treatments. Now, if you don't know anything about x and y, then what you would do is say, well, okay, what's the expected effectiveness given the range of values that we might have with some associated probability distribution? So for each of the possible treatments, little d, we work out the expected effectiveness, and then we maximize that over the different treatments available. On the other hand, if we perfectly knew these parameter values about the effectiveness, then we would choose for any particular pair XY what is the most effective treatment. And therefore, on average, averaging over all of those distributions for X and Y, it's the expected value of the max, which would give the expected effectiveness if at some point in the future we suddenly had perfect knowledge. And then there's an intermediate case where if we know X but don't know Y, then we have this nested expectation problem. So the expected value, this is expected with respect to variations in X, of the maximum over the different treatments of the expected value conditional on X. And essentially, looking at the difference between these quantities, you get the sort of economic value of obtaining more information about X in this case by conducting a medical experiment to learn more about the parameter value X. So that's the motivation here. The interesting thing from my point of view in terms of Monte Carlo methods is that we have this nested expectation problem. So if we go to the next slide, Right, so this is just a bunch of definitions. So the expected value of perfect information is the difference between the two quantities that's shown there. You know, so the one that comes from knowing everything minus the one that comes from knowing nothing. That one doesn't involve any nested expectations. So as long as you can do an order 1 cost per sample, then that naturally has an epsilon to the -2 complexity. The interesting one, as I said, is expected value of partial perfect information, which is where we get into this nested expectation. And in fact, the thing that we choose to estimate is the bottom quantity. It's the difference between EVPI and EVPPI. So if you think about this from a Monte Carlo simulation point of view, what are you going to do about the estimated nested expectation? Well, what you can do is to use some number of samples to approximate the inner expectation, and then a separate set of samples for the outer expectation. And you can see that this gets really complicated, very costly, because for each value, each sample you take for the outer expectation, you're then taking a whole bunch of samples for the inner expectation. And so that product leads to a very large number of total evaluations of FD. So if we go to the next slide, what the multi-level approach to this is, and this is what my collaborator Takashi Goda came up with, was to approximate the inner expectation on level L of the multi-level using 2 to the power L samples. Okay, and in fact, there's a particular nice trick which further improves things. So on level L, we're going to use 2 to the L samples. On level L-1, we're going to use 2 to the L-1 samples. So what we do is, as it shows here, we have F bar D, that's an average over 2 to the L inner samples. But then we take those 2 to the L inner samples and we split them into 2 halves, A and B. And we could just say, well, the level L-1 approximation will just average over set A. Or we could say, well, we'll just average over set B. But in fact, it is better to use both of those halves. So you get one value from averaging over set A, one value from averaging over set B, and then you combine those two. You take the average of those. And it turns out that that greatly improves the variance of the estimator such that the variance decays very rapidly with level by doing that. And so we end up achieving epsilon root mean square accuracy with an epsilon to the epsilon to the -2 order cost. Okay, so Takashi came up with the ideas and implemented things, and I worked with him on doing the numerical analysis for that. And we have a paper, I'll give the reference at the end of the talk. Going on to the next slide, Takashi then extended this work to expected value of sample information. I suspect there are people listening to this talk who know much more about this subject than I do. But essentially, it's generalizing those ideas, and you end up, again, with nested expectations, but now it's a much more complicated beast. You actually have this ratio of expectations. So here, you're trying to, theta are your hidden variables, y is your sample information, and rho y given theta is your conditional probability of getting y, or density of y given theta. But essentially, the ideas are carrying straight across. That again, we're doing the multi-level approximation on level L using 2 to the L samples for each of these inner expectations. So works well again. The numerical analysis gets more complicated. And then Howard Tom in Bristol provided the motivating medical application. Okay, next slide. So that was one piece of work. Another piece of work which has been with a student of mine is addressing this issue of approximating distributions in generating random variables. So there are some random variable distributions which are really expensive to simulate from. And one of the motivations for this was actually a non-central chi-square distribution, which is important for a model used extensively in finance, the CIR model for interest rates, and it links to something called the Heston model with stochastic volatility for stock prices. But even with normal random variables, there is a cost involved in converting from a uniform random variable, which is what you generally first generate, converting from a uniform distribution on the 0-1 interval to a normal distribution, and particularly for vector implementation. And so that's led to previous work that we've been building on. Next slide. I'm just looking at how the time's going. Okay. So simplest example is, again, that Euler Maruyama example, where we're generating a generating a unit normal random variable as the inverse of the normal CDF function, with the argument being a uniform random variable between 0 and 1. But suppose instead of using a sort of true normal random variable, we use an approximate normal generated by using this Q tilde function, but based on exactly the same uniform random variable. Okay, so if we go to the next slide, so this is the crudest possible approximation that you might use, which is a piecewise constant approximation. Here I've illustrated it with, I think that's 8 intervals, but you can do a piecewise constant approximation with 1,024 uniform intervals. And that's something which then is just a simple lookup table, which you can hold in the level 1 cache. And so that's a very rapid thing to execute. So you're completely sidestepping the usual problem of approximating the inverse of the normal CDF function. If we go to the next slide, this is something that is even faster on vector chips, and in particular, Oliver's work was partially supported by ARM, and the Fujitsu A64FX chip. So this is the one in the supercomputer that was being discussed yesterday. So that's a vector processor. And here we're breaking the interval from 0 to 1 into intervals of different size with piecewise linear approximation on each interval, and the intervals get smaller as you get towards the two ends in order to resolve the singularity. And with this number of intervals, the lookup table, rather than being within a cache, it's actually doing a lookup within vectors. And so it's to do with indirect addressing within the vectors. And this executes really well for vector systems like the A64FX. And as you can see visually there, there's a good level of agreement. So if we go to the next slide, so this is just a straightforward application of the two-level multi-level. If we're doing an SDE approximation with a fixed number of time steps. And you can do the analysis to show that the variance of the difference between the simulation using the true normal versus the simulation using the approximate normals, that variance is proportional to the variance of the difference between the true normals and the approximate normals, so difference between Z and Z tilde. And so you can get significant savings if that variance of the difference is very small and the cost of doing this internal vector lookup is much cheaper to evaluate than the standard inverse normal CDF. If we go to the next slide.
Mike, maybe another minute.
Oh, okay. Basically, the whole thing can also work in the context of doing the full multi-level in time as well as multi-level with respect to this approximation of the normal random variables. So if you're interested in learning more about that, I can give you further details later. So let's just move on. Next slide. The same thing also extends over to doing the reduced precision calculations. That these days on the vector GPUs, you can do half precision 4 times as fast as single precision. The single precision is considerably faster than double precision. So there's a lot to be gained by doing low precision computing. And again, the multi-level correction ensures that overall you don't lose accuracy in the estimate that you end up with. Next slide. I think it's just, oh yes, just to mention in terms of ExCALIBUR, I've got a postdoc who's now looking at issues to do with reduced precision computing for PDEs to understand the errors that come out of that. And again, you can do a stochastic analysis of models of round to nearest rounding errors and the way they accumulate over multiple time steps. Then the final slide is just the list of references. So if anybody wants to learn more about any of these topics. Thank you.